we are ready to go.
Awesome. All right. Thanks to everyone who's stuck with us all day. We are in the last session of part 1 of the Big Data Conference 2020. Our last speaker for the day is Amin Saberi. He's a professor of management science and engineering at Stanford, and also at the Institute for Computational and Mathematical Engineering, and by courtesy in the Department of Electrical Engineering. Yeah, you heard that right. He's in 3 different departments. He's a recipient of the Terman Fellowship and also the Sloan Fellowship, just like our last speaker, and has won a ginormous number of Best Paper Awards. He was also the founding CEO and chairman of NovaEd Incorporated, which is a social learning environment, which he designed in his research lab and is now used at Stanford, Berkeley, Michigan, and a number of other institutions to deliver courses to hundreds of thousands of learners. And we're adding, now, to his online, content delivery platform by, by another fraction of that. I've known him for a long time. He's totally excellent. But it turns out I was looking, I was looking at his website to check all of the, the details and make sure I got them right. It turns out I've known his work even far longer than I've known him, because one of the very first papers I ever read in Econ CS was AdWords and generalized online matching, which I did not know it. I haven't looked at it in a decade. I did not know at the time that he had written it. So I've been a fan of his work, and I'm a great fan of him, and very excited to hear him join us with matching in dynamic environments.
Thank you for inviting me and for your introduction and for making me sound, old. I'm going to talk about matching in dynamic environments. Thanks also for sticking with me until the last talk of the day. It's still morning here, but I understand that it's afternoon for most of you. Matching is the most central problem in algorithm design and combinatorial optimization. It has roots in the works of mathematical giants like Euler and Kirchhoff, and it's been crucial in the development of theory of computing. Edmond's paper that gave an algorithm for finding matchings in general graphs introduced this notion of good algorithms, what we now call polynomial time algorithms. And Karp's paper that reduced 6 central combinatorial optimization problems to each other, problems that now we call NP-complete or NP-hard, included 3-dimensional matchings as one of the 6 problems. And now with modern applications, sort of in design of modern online markets for the allocation of advertising or for ride sharing or ride hailing applications or online retail, we are seeing new applications of matching and sort of very intriguing questions and open problems arising in that context. One of the features of these online applications, these recent applications, is that the graph on which we have to find the matching is not given to us completely. We receive it bit by bit, piece by piece. And we have to make decisions about who to match to whom with no information about the future or with uncertain or incomplete information about the future input. As Scott mentioned, I've been working on these problems for a while, applications in online advertising, ride sharing, matching, and inventory management. This is a small subset of, papers I have looked at. I'm going to focus on applications to ride sharing and matching with deadline today. I'm not going to survey a lot of algorithms and a lot of results for you. I'm going to do the opposite. I'm going to tell you about a lot of open problems, a lot of problems we don't know how to solve. But I think they are interesting mathematically, and also in terms of their applications, they have potential for impacting a young industry. All right, so let's get on with it. I'm going to talk about online matching with deadlines. So if you look at the picture on the left, it's the additional life expectancy in terms of number of years for someone who has a kidney failure. So like if you're in your 30s and you have a kidney failure, you have around 10 more years on dialysis. So essentially, this gives us 10 years to find you a kidney, to find you a match. On the right-hand side, it's the Uber app. So if you request, for a ride share on one of these ride-sharing applications, Uber or Lyft, typically the app gives you a window. So it gives you essentially like a countdown of, it gives itself 3 minutes or 5 minutes to find a match for you. This is probably someone who's going, the same route or a similar route. So in this window, the app can look at all the rides in your vicinity and find the one that's the best match for you. So in both cases, there is this window in which you have to make decisions about how to match vertices. Another similarity that these two applications have is that in the first one, in the case of kidney matching, improving the quality of matching, coming up with a better algorithm will lead to higher quality of life, increased life expectancy. On the right-hand side, in terms of ride-sharing applications, if you improve the matching, it will lead to less driving time, less waiting time, and essentially, again, improving the quality of life. Let me tell you a simple model that tries to capture this matching with deadlines. So the model that I'm going to work with is that we have n vertices and a weight function, wij, between every pair I and j. So this weight function is arbitrary. Imagine it's even determined by an adversary. You have these n vertices, you have the weight function, and then once the adversary or your instance is determined, then vertices arrive in a random order, one at a time. Sequentially they arrive, the first vertex, the second vertex, and then each vertex stays in the system for d time steps. So from the time it arrives, it stays for d steps, and then it departs. Now, two vertices can be matched to each other if they are present at the same time. So let's say this vertex arrives and leaves at after d steps. The other vertex represents an interval. If these two intervals intersect, you can match them with each other. So the vertices arrive one after another. You match them. At the end of the the process, you have a matching, and your goal is to maximize the expected weight of the matching. Is the problem clear? And let me take a look at the chat. I see a lot. Okay, very good. Now, I'm going to be thinking, trying to find an online algorithm. So when you're, in this context, an online algorithm has to make irrevocable decisions on how to match the vertices. So when a vertex arrives, you find out about its edges or the weight of the edges between that vertex and all the other vertices, how much value you will gain if you match that vertex to any of the other vertices that are present. And with that information, you have to make a decision in the lifetime of that vertex, whether you match that vertex and who you match it to. So you have to make this decision with information only about the vertices that have arrived so far. I know we have a big audience, but I still like to ask a question to make sure that the setup is clear. So can you suggest, one or two simple or natural algorithms for the problem that I just proposed? And you can enter it in your chat or in the Q&A. So any suggestions as to, for this problem, if I give it to you, let's say you're, doing this for Uber, and the vertices arrive and they leave, and you want to come up with an algorithm on how you match the vertices as they arrive. Yes, so Scott is suggesting the greedy algorithm. When a vertex arrives, you look at all the vertices that are available, see what's the other vertex with the highest, if there's another, look at all the vertices that you can match this vertex with, which one gives you the highest value, match it with that one. Or, you set up a threshold. If as soon as you see two vertices whose, two vertices I and j, for which wij is bigger than threshold, you match them. Excellent. So, I have another one that, sort of someone suggests dynamic programming. And that's a great idea. That's an interesting idea. But for dynamic programming, you have to have some information about the future arrivals, so you can actually build your, dynamic programming table. And here I'm not assuming that I know what happens in the future. That makes the dynamic programming difficult. Now, if you had some stochastic information, you could think about that, and then think about the size of the table that you make in your dynamic programming. All right, great suggestions. Before I go to my proposal, let me tell you also about this benchmark, the optimum offline algorithm. One thing that you can do is that you can wait until the very end and see who has come and who sort of at what time and left, and what was the weight of the edges between vertices that were available at the same time, and you can find the maximum weight matching there. So that's an optimum offline. That's not necessarily achievable in the framework that we are discussing, but we're going to use that as a benchmark. We are trying to get as close as possible to that. The competitive ratio of an online algorithm is the ratio of the performance of the algorithm over the optimum offline. So you look at how your algorithm did. You look at the best you could do if you had all the information available to you. The ratio of the ratio of these two numbers is the competitive ratio of your algorithm. And we look at the worst case instance to determine the competitive ratio. So actually, the algorithm that I'm going to look at is the batching algorithm. The algorithm is, as follows. Every d+1 steps, you look at all the vertices that are present, and they are all, eligible to be matched with each other. So like, let's say you start at time 1 until time d+1. Nobody has left yet. You can match anybody to anybody. You find the maximum weight matching there. You clear the market to the extent that you can. You find the maximum weight. Then you wait another d+1 steps. These vertices that you consider now, they all expire, they all depart. You will have another d+1. You find the maximum weight matching again, and you repeat this. So this is similar to, say, a platform like Uber. Every 2-3 minutes, they look at all the match requests and find the best way to match all of them, and then do nothing, and then again come back in 3 minutes and clear the market. Or in the context of kidney matching, you will have a panel of doctors who will meet frequently, look at all the possible sort of matches between patients to each other, or patients to kidneys, and they they decide who should be matched to whom. So it's a simple, it's a natural algorithm. It's not actually too far from what's implemented in practice in the ride-hailing application. And here is our question, or here is our conjecture, that batching is the optimum algorithm from the point of view of competitive ratio. So, you can come up with different algorithms, some more, some simpler, some more complicated. But when you look at it from the lens of competitive ratio, batching is the best thing you can do. Is the question clear? And I have the question of what is the smallest possible D. D depends on your application. For example, in the context of ride sharing, you can't really ask people to wait for half an hour or an hour to be matched. You can ask them to wait for a few minutes. Now, in the case of, let's say, allocating organs, allocating kidneys, probably the waiting time of a few months to a few years is reasonable. All right. So that's the question that I have thought about for quite some time. Seems like a very nice question. I don't know I don't know the answer to it. I don't know how to prove this. The best we can do is to prove the following: that the batching algorithm with batch sizes d plus 1 is at least 0.27 of the optimal, and no algorithm can achieve a competitive ratio better than half. My conjecture is that batching asymptotically gives you half of the optimal, and that's, as we have proved, is the best you can do. But we can only prove something that's close to 1/3, 0.27. In the next 10 minutes, next 10 to 15 minutes, I'm going to give you an idea of the proof of this theorem. The proof is actually simple. If I do my job well, and if you listen closely, you will get the outline of the proof. Not all the details, but most of the sort of the main steps of the proof. So the proof actually has 3 steps. First, we reduce the analysis of this online algorithm, reduce the analysis of batching to a graph covering problem. So we turn it into a graph theoretic problem as opposed to an algorithmic problem. Then I'm going to show you 2 amplification gadgets that reduces the problem from large n to a small n and from large d to a small d. So essentially it says if you prove the theorem for a small n and a small d, you can get it for large, arbitrarily large n and d. And then once we have that, you can, for a small n and d, you can actually use computer-based proof. We use LP. Essentially, we use a factor revealing linear program to tell us, to give us a bound on the performance of the algorithm for a small n and d. And let me introduce, sort of some notation. For a graph H, M of H is the maximum weight matching on H. And then if I have some graph H that's unweighted, if I apply a vector W, a weight vector to it, essentially every edge in H, every edge ij in H is going to get weight Wij. I'm going to also think about graph operations. Like if I say add to graph, essentially you're adding their adjacency matrices. You're superimposing the 2 graphs on top of each other. And if I say H is bigger than or equal to G, means that if G has an edge, H also has an edge, or the number of copies of an edge ij in H is bigger than or equal to the number of copies in G. Okay. So let's do the step 1, the reduction to a graph theoretic problem. Think about a binary weighted graph, a simple graph in which you put all the vertices on a line according to the permutation, according to their arrival. So you put the first vertex that arrived, then the second vertex, and so on. And then for every vertex, you attach it to all the vertices that arrived up to d steps before and up to d steps after. So these are essentially all the vertices that can be matched to this vertex. That gives you, sort of this, this, graph that's essentially line to the power d. Now, the optimum of line, the algorithm that finds the optimum solution in hindsight, essentially finds the maximum weight matching in this graph. Looks at all the pairs of vertices that are eligible to be matched to each other, finds the maximum weight matching there. So that's the value that optimum offline collects. What about batching? Well, batching, looks at every d plus 1 steps, and there, everybody is eligible for everybody. So essentially, it divides your, graph into this complete graphs of size d plus 1, and in each one of them finds a maximum weight matching. So if you look at the the value that your algorithm, the batching algorithm collected for the arrival permutation sigma, it's the matching, the maximum weight matching in the batching graph in this, sort of collection of complete graphs once you impose the weight W. Now, here is the crucial observation that helps us a lot. Define a graph cover. So say a set of graphs H1 to HK is a cover for H. If once you put these H1 to HK on top of each other, it covers H. Essentially, it has as many edges or more edges than H in every location. Now, that's a sort of simple cover. I can also define a fractional cover in which instead of adding up adjacency matrices, I look at a linear combination. So I say if there are these k permutations, sigma 1 to sigma k, and non-negative lambda 1 to lambda k, such that sum of the lambda k is equal to alpha. And then if I look at batching for permutations sigma 1, sigma 2, all the way to sigma k, look at that linear combination. So take batching, multiply them to these numbers, and then put them on top of each other. It covers the optimum, solution for some permutation. Let's say identity. Then batching is 1 over alpha competitive. So essentially, it says look at the optimum solution for some permutation. Let's say the identity permutation. Then look at batching for a bunch of different permutations, and then use those graphs to cover the optimum. This is sort of a standard approach in polyhedral combinatorics. It says if you can do the sort of the covering, then essentially the maximum weight matching that you find in this collection, the same convex combination is going to be bigger than or equal to the maximum weight matching in optimal. So the proof of this is actually simple. It's just a change of order of sum and expectation. All right. But now something very interesting happened. So instead of worrying about all these vertices arriving, departing, the analysis of the algorithm, I have a simple problem. I have one graph, and then I have a, for the optimal graph, and then I have this batch for different permutations, and I'm trying to find the best cover for the optimum using these batches. Let me look at chat. Yes, I mean, actually, Clement is sort of commenting. This is like a basis. Yeah, it's like a basis, but I need the lambda i's to be non-negative. So it's essentially I'm looking at the convex hull of these, and I want to make sure that the convex hull has the optimum solution inside of it. Very good. So now I have this graph cover problem. I want to, sort of, I'm going to use two techniques to deal with it. One is that I'm going to do this, sort of cover from a small n. I'm going to have this amplification gadget that takes a cover for a small n and gives me a cover for large n. And I'm going to do this for periodic permutations. So a permutation is, for some p, is p periodic if it repeats itself. So sigma of I plus p is sigma of I plus p. So you have a pattern, and every p steps it repeats. So imagine I have a periodic permutation that covers my, sort of, well, the optimum solution is, I presented it on a line, but now it's simpler to think about a cycle. It will give me a more elegant solution. So imagine I have this cycle that represents the optimum solution, and I have a cover that's actually cover using p-periodic permutations. The batching is corresponding to p-periodic permutations. If I have that, I can open it up and I can repeat the same pattern. So essentially, it tells me that if I have an alpha cover of CD of n, I can extend it to an alpha cover of CD and n prime when p divides n and n divides n prime. And even if they don't divide, and if p doesn't divide n and n doesn't divide n prime, for large enough numbers, the error is small. So in the paper, we actually have a more robust version of this lemma, but it's easier to present it in this form. Then imagine I have this cover for a small d, I want to produce a cover for a larger d. What I can do is that I can duplicate the vertices. I look at one cover. For every vertex, I'll put 2 copies that I can triplicate and so on. So that will tell me that the cover of the contracted graph can be mapped onto a cover of the original graph. And again, I have a small loss if d does not divide d prime. So essentially, I have these gadgets. They tell me if I have a small cover, if I have a cover for some alpha for a small n and d, they will produce a cover for me for larger n and d. Now, I need to prove, find a small cover for d that's a small. I can do that, as Clement mentioned, sort of using a linear programming approach. Now, even for d equal to roughly 50, you have 50 factorial variables, and that makes it very hard to solve the problem. But there are several techniques that you can apply when you are solving a linear program that's as nice as that. We managed to find a bound that's, alpha d is less than 3.58. And for d bigger than 50, we use those amplification gadgets. 1 over 3.5 is around like 0.279. So that gives me the competitive ratio that I claimed at the start of the talk. So that's a short proof for the theorem that I just presented to you. Are there any questions?
If people have questions, they can put them in the chat or the question answer.
Okay, very good. So now this one was, sort of this algorithm was designed under this assumption that the vertices are arriving at random. And I guess, some of the questions actually mention, sort of, what if we don't have that? What if the arrival is adversarial? So vertices this time arrive sequentially again and wait for d steps, but the weight of the edges and the order of vertices is arbitrary, and it's decided by an adversary. So essentially, you have the algorithm, you make the decisions about, how to match these vertices, and then the adversary is looking at your algorithm and decides what to send as the next vertex and what the weights are. So if you look at this example for n equal to 2 and d equal to 1, imagine the first vertex arrives, then the second vertex arrives, and then you observe that if you match them to each other, you will have a gain of 1. Now, d is equal to 1. So by the time the third vertex arrives, the first vertex is going to expire. So let's say you decide to match these 2 vertices with each other. Then the adversary can send you, make this x equal to a very large number, let's say infinity. And if you don't match these 2 vertices, then the adversary can set x equal to 0. But that simple example tells you that no deterministic algorithm can have a bounded competitive ratio. The best thing you can do is that at this point, before vertex 3 arrives, toss a coin with probability 50% match them to each other, with probability 50% not match them. And that actually shows that no algorithm can get a competitive ratio better than half. Now, can we get the competitive factor of half? We can't. We can get something close to it. We have an algorithm that gives you a competitive factor of 1/4. And again, getting this upper and lower bounds closer to each other or finding the right number is an open problem. Let me show you just like the basics of the algorithm that gives you factor 1/4. So as I told you, for this middle vertex, you have to decide randomly whether it's gonna get matched to what's available now or wait for something that's going to that's going to arrive later. So in fact, that's what we do in our algorithm. We divide the vertices randomly. Half of the vertices are gonna be patient. They get matched at the time of departure. And half of them are gonna be impatient. They're gonna get matched before the departure. So for a vertex, you toss a coin, you decide Is it going to be waiting until the very last minute, and when it's about to expire, look at all the options and get matched to somebody? Or it's going to be matched to one of these vertices who waited until the last minute before their expiration? So once you know which vertices are patient and which vertices are impatient, essentially you're solving a bipartite maximum weight matching problem. And for that, you can use existing algorithm for online matching with free disposal, or do what we did, a primal dual algorithm for analysis of the ascending auction. Now, this maximum weight matching is actually a factor half. By dividing the vertices randomly, you have to guess both sides of an edge correctly. So you will get each one of them correctly with probability half. So that will give you 1/8 of the optimum solution. But you can do this a little bit better. You can postpone the partitioning. You don't have to decide in advance who's going to be patient or impatient. So essentially, we create 2 copies of each vertex. One is patient, the other one is impatient. And you flip a coin at the very last minute and you propagate your decision. I don't want to get into the details of the algorithm. It's called postpone greedy. As I told you, at the arrival of a vertex I, it creates 2 copies, PI, patient I, and impatient QI. And patient vertices are only compatible with impatient vertices that arrive before them. You use a greedy algorithm, as Scott suggested, for your matching, and then when I is about to leave, you decide, whether your vertex was actually patient or impatient. We showed that this algorithm, this postpone greedy, is a quarter competitive, and our lower bound is half, as I mentioned. The gap in between is an open problem. Closing this gap is an open problem. All right, good. Let me take a quick look at the questions and then. So I have one question about the earlier result that I showed you that uses a linear programming proof for the cover. And the question is by Ronald asking, is there another proof? I certainly hope so. I like to see, I think there must be a more elegant proof, maybe using probabilistic method that gives you the factor half without this, amplification gadgets and linear programming. This technique of using factor revealing LPs, it's like something that we came up with when I was a PhD student. I have a tendency to use it, and I have a tendency to use it a lot. I bet there is a better proof. I bet there is a more elegant proof. Okay, let me tell you about 2 extensions. These are more recent extensions with my colleague Marco and a PhD student at Stanford, Matt. So I talked about matching only 2 vertices to each other, but as you have probably experienced in ride sharing, you can have more than 2 people in the same car. Sometimes you have 3. So then you don't have a graph matching problem, you have a hypergraph matching problem. And also, this medium or high capacity vehicles, essentially, minivans or buses that match multiple people, put them in the same car, and sort of take them on the same route. So there's a generalization that tells you, sort of how to find the optimal matching there. There is another extension that I'm really excited about. This is with Yiding Feng and Rodney Azadeh. So when we were doing these batchings, we could have sort of taken into consideration what happens in the next step. So imagine in this batch, when I'm making decisions about who to match to whom in this batch, I have some information about what's going to arrive in the next one. So let's say in this batch, I have all the passengers who have accepted the sort of the price, and they have requested the ride. I have to match them to some car. And then in the next batch, I have already given a price to the other customers who have just entered their destination. And I know with some probability each one of them is going to accept. So when I'm matching these passengers to cars, I can take into consideration, well, you know, there is someone nearby who's going to make another request, and that's going to impact my matching decision. So with that additional information, the problem actually becomes a little bit simpler, and and we came up with an algorithm that gives you the optimum competitive ratio of 3/4. So there you can actually get an algorithm that gives you a much better solution. That information is actually quite useful. Now, I have showed you algorithms with competitive ratio of 1/4, half, in this case 3/4, and you can rightfully object that these ratios are not very meaningful when you're talking, when you're thinking about applications to practice. Like coming up with an algorithm that gives you 1/4 of the optimal solution for, an application like Uber is just not acceptable. So are any of these algorithms useful? Are any of these ideas useful? I have been actually fortunate to work with people at the marketplace group at marketplace data science group at Uber. And over the past year, Uber actually did a completely new architecture for its pricing and the way it does the price search. And we came up with an algorithm that uses actually this, sort of matching based ideas for, completely changing the way Uber does its price search. And I'm very happy. I'm over the moon that it's implemented at Uber and it's, tested, and it gives significantly, substantially better results. I can't really tell you about the details. It's with, but we are hoping to get the release, and the paper is forthcoming. So hopefully at a later opportunity, I'll tell you more about how it's implemented in practice. Let me take a look to see if there are any questions.
Actually, can I jump into the quick question while we're...
Absolutely.
Okay, awesome. So I've been wondering, how much better could you do if you had like a strong prior, or even better if you had sort of like an online prior, right? You know that if there's, one call, we'll use the Uber example. If you know that there's one call for a ride at a given location at a given time, it's likely that there'll be another one soon thereafter, or something of the sort.
Yes, so we do have some information in the sense of, for example, we know which users have opened their app. And based on that, we can, make a guess, what's the likelihood that they actually do make a request.
Yep.
But that gives you a window into the future that's only like minutes away. If you want to predict, what's going to happen, let's say half an hour from now, you can do it only at the aggregate level. So let's say I can tell you, in this zip code, roughly how many rides I'm going to get, or in this city. But in order to do the pricing and matching, you need it at a very granular level.
Right.
So that information, still we have, it's very hard to use it in practice. It's very hard to use it to inform matching and pricing right now.
I see. What about the possibility, again, this might just be a subcase of the answer you just gave, but what about the possibility that you sort of know when there's a bunch of like high weight matches to, sort of high weight edges that appear, it's likely there are other high weight edges that are sort of going to appear nearby. And so you don't know where they are or when they're going to be there, but your algorithm could sort of take advantage of the fact that, sort of there's serial correlation in who shows up.
Yes. So you can definitely, in predicting the traffic, like sort of predicting the, sort of the demand or supply in the next, sort of few minutes, you can also use this momentum and say, oh, it's increasing. So I expect that, it's going to, look at the first or second derivative to make your prediction better. Absolutely. What I was saying is that we can't predict the future, let's say in half an hour or an hour well enough to inform our decisions right now.
Cool. Thanks.
Oh, of course. All right. So I still have a little bit time, but let me tell you just about a few open problems that I mentioned so far. One is if batching half competitive. I showed you 0.27. My guess is that half is the right number. Or if we do the opposite, we let batch sort of go 2D plus 1 steps in the future, then can we get sort of something that's as good as optimum for these steps in the future. Again, the best competitive ratio under the adversarial model, I showed you upper and lower bound, but we don't know the number. You can also think about variations in which there is a cost for waiting. So I assume that everybody can wait a certain amount of time. But let's say, some people can wait less, some people can wait more. Instead of making that a constraint of the problem, you pay for it in terms of costs, and you take into consideration different sensitivity to waiting. This is definitely the case in the case of organ matching. Now, I'll come back to this. This question of whether competitive ratio a good benchmark. So I gave you an algorithm. I said, here's the best thing you can do. What's the let's look at the ratio of the two. Is this the right benchmark? Is this leading to the best algorithm? I think as online algorithms find more and more applications, we need to take a second look at our paradigms and benchmarks. A lot of times these benchmarks are so crude that they won't be able to differentiate between several algorithms. Some do better in practice and some do worse. So this should be part of an ongoing conversation between computer scientists, economists, data scientists as to how do you measure the performance of the algorithm besides actually running it on the data and seeing it works well on the past data and the current data, as opposed to, the circumstances that you cannot predict in the future. All right. Now, I told you about batching. I told you about batching with some information about the future, like using the information about the next batch. Let me tell you about this. What if you extrapolate and you say, even I have information about the next batch and then the one after that, the one after that, and so on, like what Scott was suggesting. Now, my answer to Scott was that we can't predict the demand and supply even in sort of 15, 20 minutes from now. But let's say if we did, so somebody came up with this amazing machine learning algorithm that could tell me exactly what's going to happen, or with some confidence bound. So I'm going to assume that I have this graph G, A, B, and E. So you might think about maybe the A side is fixed. On the B side, for every vertex, I have a time of arrival. So I know I'm going to get a request and a probability of arrival. So then I know in this location, half an hour from now, 7 a.m. in the morning tomorrow, with some probability, I'm going to get a request. And I have this lineup. And then at every time, the algorithm observes which subset of vertices with ti equal to t have arrived, and has to decide how to match them immediately, right? So this way you can, look at the information that's certain, that's available in front of you right now, make decisions, and then you, over the, sort of an infinite, let's say, horizon, you have some information about the future. And the goal is to maximize the expected size of the matching. Now here, and then, one of you suggested that you can do dynamic programming. You can actually, do a dynamic programming here, but it's going to be exponentially large. The size of the table is going to be exponentially large. So it doesn't seem to be, like the, sort of a very, at least computationally efficient way of doing it. So with Christos Papadimitriou, we looked at this and we observed that actually this problem that we call ride matching is P-space complete. So that's one level harder than NP complete problems. So this is actually the problem, sort of the reduction from a stochastic satisfiability. Typically, a reduction sort of, if you look at the vanilla satisfiability problem, you're given a binary formula, and you're thinking about the assignment of true and false to variables that you're looking for an assignment of true and false to variables that make the formula true. This stochastic satisfiability is different in the sense that first you can set a value, give a value to x1, then the nature is going to toss a coin and set a value for x2. With 50% probability is going to be true, with 50% is going to be false. Then you set x3 and so on. And you're playing this game with nature, and your goal is to make sure that the probability that the formula is satisfied is at least half. Deciding whether this is possible or not is p-space complete. And our problem is also as hard as a stochastic satisfiability. Therefore, that's also p-space complete. This should be reduction from. On the flip side, the positive result, we show that if the compatibility graph is replaced by Euclidean distances, then there is a polynomial time approximation scheme for the problem. So, so doing this over a long horizon has challenges both in terms of prediction and also it's computationally hard. All right, so let me conclude. I hope I have convinced you that this field has a lot of interesting open problems, algorithmic and combinatorial. In general, if you look at ride-sharing applications, you look at rider pricing, driver pricing, how you match rides to drivers, how you match rides to each other, driver positioning, scheduling routes. And also this is, sort of generalizing that for mid and large capacity vehicles. They reduce to a lot of classic algorithmic and combinatorial optimization problems, like online matching that I talked about, or facility location, price collecting, traveling salesman problem, and the Bayesian selection problem. I was joking that, every old problem is new again. And because of the size of the problem and the granularity of the data that we have available to us, we can try new and interesting algorithms. And this application has its own nuances that sort of make the algorithm design more challenging. And there is immense potential for impact, both when you think about policy questions like platform competition or how to protect labor or protect consumers, and more classic optimization questions, how to reduce the waiting time or how to reduce the congestion. But as I said before, in order to have the impact that we like to have, we need to revisit common modeling practices and standard paradigms for evaluating the performance of algorithms. If you have an algorithm that has the optimum competitive ratio for the problem, it doesn't mean that the algorithm is implementable. There is a lot more very interesting work that has to be done for the algorithm to be actually useful and usable. And coming up, sort of refining and revisiting these paradigms and benchmarks is something that's going to be very useful for the field. All right, let me see if I have one question.
Awesome. Super cool. Yeah, more questions. We have more time for questions. There seems to be one or a partial question in the chat right now, but if you have more, please throw them in. There we go.
The choices X. I'm not sure when you say the choices X seem to be dependent. I'm not sure what you mean. How best can matching be done for independent choices? Perhaps, Ronald, you should feel free to send me an email and elaborate on your question, and I'm happy to answer.
Further questions? I know we covered a bunch during the talk, but happy to get more.
Okay,
maybe
it was a pleasure. Thanks for all the questions during the talk, and back to you, Scott.
Yeah, I was saying, and thank you for joining us. No, I mean, totally fantastic. And I forgot to mention earlier, thank you especially for joining us in the midst of everything that's going on outside at the moment in California. We really appreciate your making time to talk with all of us in the midst of it. let's thank Amin, and I will see all of you tomorrow, bright and early, or late in the evening, or at a middle of the day, depending on where you are around the world tomorrow for Big Data 2020 Part 2. Thanks so much. And yes, let's throw some more thanks in the chat. It's a great trend.
Thanks, guys.
Thank you.